Okay, here's 8.6, which is about e and the natural logarithm. Now, something pretty nuts is going to happen here, and stay with me, it's pretty crazy. Let's talk about the compound interest formula, which is 1 plus r over n to the nt, which was also multiplied by your starting principal, whatever that starting amount was. Well, we are going to take that formula and ignore the starting amount for a second, because we just want to deal with the growth. And let's make the interest rate just 1. So we're going to have 1 plus 1 over n to the nt. What I'm also going to do is ignore time. Let's not worry about time right now. I want to show what happens if the number of times you compound, which is n, if the number of times you compound increases. Because the math here is interesting. This number, 1 over n, continues to get smaller as n gets bigger. Right? 1/3 is bigger than a fourth, which is bigger than a fifth, so it keeps shrinking. But the power here keeps growing. So this whole thing, this whole parenthesis, will keep getting closer and closer to 1, but never actually reach 1, because of the asymptote at 1 over n. But this power will get enormously large as n gets really big. So if you have 1 plus 1 over 2 to the second, and then 1 plus 1 over 3 to the third, the question becomes, is this really growing or shrinking, and how does that work, and how does that look? So here in my calculator, in the y equals menu, I've typed in 1 plus 1 over x to the x, which is the same as having these n's. And I'm going to show the table of how this grows. So if n is 1, 1 plus 1 over 1 to the first is 2. Like if this is the number 1, you get 1 plus 1, which is 2. 2 to the first is 2. And if you get, as x grows bigger and bigger, you'll see this starts to grow bigger and bigger. But it starts growing by less and less and less over time. So there's 3, 4, 5, 6, 7. And suddenly we stay in the 2.5 range for quite a while. And then here's 2.6, and we'll stay here for quite a while. But the growth is always shrinking, because this over here is always approaching 0. So let's count a little faster. I'm going to change my table to, instead of counting by 1s, to count by 10s. Stay in the 2.6 range for quite a long time. In fact, is it even here we're at yet? Now we're at 2.7. Okay, so now instead of counting by 10s, let's count by hundreds. And you can go 18, 118, 218, 318. We barely get past the 2.7 when we get to 618. One last example. I'm going to start at 1,000 and count by thousands, and it barely goes above this. This is going to be our limit. Okay, this value isn't going to get above 2.7181 ... whatever comes after that. What's happening now is we are essentially having continuously compounded interest, meaning if it's being compounded 7,000 times, or 7 million times, or even 7 trillion times, however big n gets, this whole formula, 1 plus 1 over n to the n, is going to get very, very close to this number, 2.71828 ... that goes on forever and ever, as n gets really, really close to infinity. And close to infinity doesn't really make any sense, so that just means as it gets really, really big. This is a critically important idea. This is basically having continuous growth, meaning every passing moment growth is happening. Every passing moment we're going to take a little tiny chunk, but do that really, really, really often. And this continuous growth is so important we give it its own number. We'll call it e. E is a number that means 2.71828 ... It means continuous growth, continuously compounded interest, which I know is kind of crazy. A lot of people don't like algebra to begin with because there's already so many letters when there used to be just numbers. They prefer arithmetic. Now we're taking letters and defining them as numbers. E, whenever you see it moving forward in a function of any sort, is going to stand for the number 2.71828. So continuous growth is represented by the number e. It is the last of our absurdly important numbers. That's 0, 1, e, pi, and I. Those are the 5 kind of critical numbers that all of this algebra can be based around and off, and things can be accomplished with. There's actually a formula, an equation, that relates them all to each other, which is sort of crazy also, but we won't deal with that now. Because e is such an important number, it has its own logarithm, which is called the natural log. If you have log base e, that means ln. That's a lowercase l. So people always think it's in, but it's not. That's ln. It's a lowercase l. It means logarithm natural or something French like that. So they're saying it backwards from us Anglicans who would say natural log. They're logarithm natural. It's the log with a base of e. So we're used to seeing like log base 3 of 9 equals 2. That's a log with a base of 3. Well, log base e of 2 would just be, well, I don't know what that number is, but we'd call that natural log. I wrote that very poorly. Natural log of 2. These two expressions are the same. Now, this is all going to feel very different because you just feel like you're running out of numbers. Like the numbers are just vanishing. But e is a number, so whenever you see it, think of it that way. Like when you see pi, think of it as a number. And there's these properties of logs that are still going to be true even with natural logs. The natural log of e is just 1, because that's really the question. Log base e of e, so e to what power equals e, and that's 1. The natural log of e to the x equals x. This is an important property. It's how you cancel out, or really inverse, the exponential properties happening with e. E to the ln x equals x, and then here's just the properties of logs done with natural log instead of log. A key idea here though is if you ever see ln and you're not sure what to do with it, you can just turn it into log base e. You can write it that way and think of it that way. If you're really desperate, turn that in and just write log of 2.718. But you need to get to the point where you just see ln and know what they're talking about. So let's do some work with this, and I can't type very well, so I had to erase some stuff. An account earns 2.25% annual interest, compounded continuously. What that means is every year, they're going to give you 2.25% interest, but they're going to break it up into really, really, really tiny little parts, and do that really, 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 really often. And if you get embarrassed by hearing me say really so much, you know, I'm embarrassed too, so thank you. If the account is worth $870 today, how long until it's worth $1,000? So it's not going to grow very much, or it's going to grow by $130. But this is never an addition or subtraction game, it's always a multiplication game. We used to deal with this property, or actually this formula, 1 plus r over n to the nt. But that was if the compound interest was happening with some kind of like understandable frequency. Now we know that this n is really becoming infinity. It's like we're plugging infinity in for these n's because it's happening continuously, meaning every passing instant. And we know that this whole thing equals e if n is infinity. So this actually becomes a new formula, pe to the rt. This is what you use if you have continuous interest. So that word continuous becomes very important. This one was compound. Well, it's frequency that's not continuous. So I'll just call this one non-continuous for now. So the question becomes, how long until it's worth $1,000? Well, I'm going to plug 1,000 in for y, 870 in for p. E is just the number e. The interest rate was 0.0225. We're trying to solve for this time t. The first thing I'm going to do is divide both sides by 870 to get the exponential part by itself. That gets me some number that I'm not going to calculate yet. The next thing I'm going to do, and I'll do that way over here, is take a natural log of both sides. So the natural log of 1,000 over 870, so much easier if it was 870 over 1,000, but whatever. 1,000 over 870 equals the natural log of e to the 0.0225t. Sneak it in there. It's no better. Well, on the left side, we just have to calculate this. on the right side, all we get is 0.0225t. Because the natural log and the e are their inverses, so they undo each other, and we're just left with this. So I divide both sides by 0.0225t. Nope, just by 0.0225, not the t. And now I'm going to run the calculation. I did this off screen because my calculator on the computer is running very slow. This becomes 6.189, which we would call about 6.2 years. So that's just continuously compounded growth. Make sure that you use this formula whenever you see the word continuous. So this also leads into half-life type problems. So some substance that I made up decays from 24 milligrams to 16 milligrams in 10 months. So we just did some measurements of this substance as it was decaying. It's decaying pretty quickly here with that timeline. Well, the thing about half-lives is, even though we tend to talk about them in terms of how long it takes for half of it to decay, it's always decaying. It's like every little cell, every little bit of matter, every atom is doing its own decaying at the same time. So no matter how big or small the object is, the quantity you're working with, all of it is decaying all the time. And because it's an all the time thing, we use E. So we've been seeing y equals PE to the RT for money, but we often just typically see A e to the kt. A is your starting amount, and k is called your growth or decay rate, growth or decay constant. This, again, is involving E because it's happening continuously. So we want to try and find what this k value is in this problem. Well, this is our starting amount. This is our ending amount, and this is our time. I think I'm going to put this in years. That's 10/12 of a year, which is 5/6. So I want to find the decay value k by plugging in these numbers. I'm going to have 16 equals 24 times e to the 5/6 or 10/12 times k. I kind of wrote those backwards because this went here and this went here. But I think you can figure that out. And then I'm just going to solve this for e. So my first step is to divide both sides by 24. And I'm going to keep working off screen on a calculator. 16 divided by 24 can reduce, of course. Well, 16 over 24 is just 2/3. I'm going to reduce that. So instead of doing a half-life, I'm doing a 2/3 life. It turns out the 2/3 life of this is 10 months, or 5/6 of a year. Now I'll take the natural log of both sides. The natural log of 2/3 equals the natural log of e to the 5/6 times k. And the natural log of e is just 1. So we get the natural log of 2/3 equals 5 divided by 6 times k. I'm going to multiply both sides by the reciprocal, 6/5. And I get that I'm going to do in my calculator is negative 0.486. Now, this is actually extremely high for a half-life. I mean, this is just insane, but they're made-up numbers, so it doesn't matter. It's negative because it's decreasing. There's decay. Sometimes people even write the formula with a negative here, and they'll say negative kt like I did up here. So we would really want to say the k value is just this part without the negative, because in the formula it already includes a negative. If it didn't, then that's fine. But we're going to say, to answer the first part, find the decay value, the value of k, that k is about equal to negative 0.4866. And I don't want to I'm sorry, I don't want to make it negative, because the formula we were asked to find already has a negative in it. So there's my k value. And it says find how long until only 8 milligrams remain. So let's just go from 16, because that's where we're at right now, I suppose. Nah, let's go from 24. So I'm going to go y equals AE to the negative KT. My ending amount is going to be 8. My starting amount is going to be 24. My negative K value is now negative 0.4866558. And then my time, I don't know, so that's my T value. Solve this like how we've solved everything else. Divide both sides by 24 first. That gives me 1/3 equals e to the negative 0.04866t. Take a natural log of both sides. And inside there was e to the negative 0.4866t. And that's going to leave us with the natural log of 1/3 equals negative 0.4866t. Divide both sides by that number, and that'll give us t. I am not going to type any of this into my calculator, so you keep seeing just like this written over and over and over. I'm not going to type that into my calculator. I'm going to keep using this number here that I have stored in my calculator. This is another reason why you do all the calculations last. So in my calculator, I'm going to do the natural log of 1/3 and then divide it by that previous value that I have stored in my calculator. So I get 2.257. Oops. So it's going to take about 2.257 years. We converted this to years by doing the 10/12ths instead of doing just straight 10. So there's a very typical half-life problem. Find the value of k, then use that k to solve other things in the problem after you've set up the equation that looks like so. So there you have it. We learned a new number, which is e. Pretty crazy. It's an important number that has its own logarithm, the natural log, which is ln. Natural logs follow the same properties as other logs because they're all in fact the same thing with different bases. And anytime something is changing continuously, well, I should say changing continuously but exponentially, you know, something changing continuously exponentially, that's a tough word to spell. Sorry. If something's changing continuously and exponentially, you'll be dealing with the number e. We'll also do some half-life examples with it as you move forward. Pretty much anything that has exponential growth is done with a base of e in your pre-calc and calc classes. And it's just a super, super important and really wonderful number.